logistics. So for some reasons, you guys are taking a holiday next week, unfortunately, so we won't have class. The week after, on the 29th, unfortunately, I'm away that week at Germany, but we're going to have our amazing Rachel in the back give a fantastic lecture. So, you'll enjoy that. And then the week after, which I believe is October 6th, I would have loved to give you a great lecture, and I'm here. However, you're going to get something even better, because there is a really, really amazing work, new work by Oded Regev, who constructs a new factoring algorithm, quantum factoring algorithm. So kind of improves Shor's algorithms in some way. It's a really, really exciting piece of work. Oded is in Paris, but that's the one day he was able to come here and present his work, and it's exactly on this class. So I think what we should do, this class will move on October 6th, and we'll all go to Oded Regev's talk. It's going to be this class, it's going to be a colloquium, and it's going to be a theory reading group. It's going to be kind of all in one. It's going to have a very nice format where the first hour or so is going to be kind of a very general theory audience talk. And then we're going to have the next 2 or less hours, depending on how much he'll have the energy to speak to us. We're going to talk about kind of more details about his algorithm and his work. So that's October 6th. And then I'm going to be back. So you're going to have a bit of a break from me now, which I'm kind of sad about, but you may be happy. OK, so let's first kind of recap where we were and continue from there. So last time we defined kind of this new class of proofs, kind of going away from the classical proofs to the regime of interactive proofs. We showed the power of these interactive proofs by showing one protocol, in particular the sum check protocol. I wrote the sum check protocol kind of very loosely in that board because we're going to refer to it today again. So the sum check protocol, just to recap, it's a way to prove that the sum of a multivariate polynomial over, let's say, a small set H. You can think of H as 0, 1 as an example, over like a Boolean cube or just a bigger cube. The sum is some value over some finite field. And of course, to compute this sum takes a very long time. It's like H to the M. You need to just sum everything up. But it turns out that you can verify it using an interactive proof very, very efficiently. Assuming you have oracle access to this function, you can compute it kind of efficiently on any random element in the group, in the field. So this is what we covered last time, the sum check protocol. As I told you, this sum check protocol is really the bread and butter of proof systems. Almost every proof system uses this protocol. It's a beautiful protocol, in my opinion. And we'll use it throughout kind of this course. So if anyone has any questions about the sum check protocol, please ask. OK, and if it doesn't sit with you yet, I really encourage you to review the notes and kind of, in the website, there's also notes to Justin Taylor's a survey, which contains a very nice exposition. And also, we have now Scribe for that. So, you have various resources to look at the protocol. OK. And then we start to look at kind of applications for the protocol. The first application we got is to show interactive proof for sharp sat. And we showed this interactive. The idea was it was via this technique of arithmetization, converting kind of a Boolean circuit into an arithmetic circuit. We'll use this technique today as well. And then we departed and talked about this idea of a doubly efficient interactive proofs, where in doubly efficient interactive proofs, we really care about the runtime of the prover in addition to the runtime of the verifier. So in the classical interactive proof setting, all the focus was on efficient verification. Nobody cared about the runtime of the prover. Okay, he was for all practical purposes, we thought of him as like an all-powerful. But doubly efficient interactive proof, now the prover, of course, is more powerful. Otherwise, the verifier would do the work on his own. But we don't have all powerful things in this world, unfortunately. So we also care about the efficiency of the prover. So he's just more efficient, but we don't want his work to be crazy expensive. Okay, so that was the doubly efficient interactive proofs. And we just started, and we'll continue today, to show how we get a doubly efficient interactive proofs for counting triangles. And it was via, for counting triangles in a graph, and it was via a technique called the low degree extension. Okay? So now the plan for this class today is to look at the low degree extension. Okay? Again, this low degree extension, it's a theorem, it's written here. I'll explain it. It's again the bread and butter. That's actually, this low degree extension theorem, in some sense, is what makes the sum-check protocol so popular, so kind of important. Okay? This theorem is what gives the sum-check protocol its power, in a sense. So really together, the low degree extension theorem together with the sum-check is like everything follows from it like via corollaries almost. Okay, so we'll kind of, that's what we'll see this lecture and the next lecture. Okay, so what is the low degree extension theorem? What it says is that take any function from h to the m to 0, 1. H is just any set. It can be 0, 1 to the m, it can be Boolean hypercube, but it can be a bigger hypercube. Okay, if you're more comfortable, if it's easier for you to think of h as 0, 1, just think of it as 0, 1. Okay, so take any function from h to the m to 0, 1. So when I say any function, it's not a polynomial, it's just a set of elements. So when I say any function from h to the m to 0, 1, you should think of it as just an arbitrary sequence of h to the m bits. Okay, and I just order them like in a hypercube. Okay, so I have this sequence of h to the m bits defined by this function. And the theorem says that if you take any finite field that contains this set h, so if h, let's say, is Boolean 0, 1, you can take any finite field. Every finite field contains 0, 1. Okay, but more generally, any finite field, there exists a unique polynomial. So now we move from an arbitrary set of bits to a polynomial f from f tilde. So we call it, this is the extension. So we call it from f to f tilde, from f to the m. Not h to them, but f to them. So I extended it to f to them to f, such that if you look at the extended polynomial on the small hypercube h to the m, it really is exactly f. And this f tilde has small degree. So its degree in each variable is h, the size of h minus 1. Okay, so if you want to visualize it, here's what you should think. I have a bunch of like bits sitting on some hypercube. It can be Boolean or it can be like more, elements here. But I have arbitrary sequence of bits sitting here in this hypercube. And the theorem says you can extend this to like a function over a big field, so over f to the m, in a unique way. I don't know if I specify, it's a unique way, in a way that it extends. So on the values here are exactly as before. And the degree of this polynomial in each variable is exactly h minus 1. Okay, this is the theorem. By the way, in the case where h is 0, 1, then the degree in each variable is 1, because h is 0, 1, so the size of it is 2, degree 1. This is often called multilinear extension, because the resulting f tilde is of degree 1 in each variable, in which case it's called multilinear. Okay? Any questions about what this theorem says, the meaning of this theorem? Okay, so we're going to prove this theorem next. And then we're going to go back to this counting triangles, which was just kind of a motivating example. But what the focus is really this theorem. And before I go into the proof, I want to say why this thing is so powerful is that it allows you to go from an arbitrary sequence of bits to kind of a polynomial, which is of low degree. And a polynomial of low degree has a lot of structure. And that kind of really helps us. For example, once you have polynomials of low degree with structure, we can apply sum-check protocols. Okay, so that's kind of the way you will often use sum-check protocol. We're first going to go to we have an arbitrary sequence. We're going to take the low degree extension, and now we can kind of argue, we can then use the sum-check protocol. Okay. Any questions before we? Yeah.
There's another way to get these guarantees, maybe a not for arbitrary functions. Right, so you take the, you arithmetize.
Arithmetize.
F.
Yeah, right. Mm-hmm.
So that should give you a low-ish degree, well, not a low degree, if the depth of F is small, right? Degree or the Boolean hybrid
okay.
of the original function.
So what you're saying is good. Let me just repeat what you're saying. What you're saying is if F is not arbitrary, but actually is kind of a circuit, an arithmetic circuit with and and or, with addition and multiplication, and it's very low depth, like log depth, let's say, or let me call it depth D, then just kind of think of it as over a big field, especially if it's 0, 1. You can think of it over a big field. And then the degree of this thing will be like 2 to the depth. You're right. But 2 to the depth, So you're right. And so actually for sharp set, that's what we did. How did we use the subject? That's exactly what we did. But then you need to assume a lot of things. You need to assume that so you're right. If you start with an F that has structure, that it's very, very low depth, or like the degree is very small, then you're done. You already have it. But what this is saying for any sequence, so any sequence of bits can be arbitrary. You can kind of put it in this way.
So I was just sort of referring to the uniqueness claim. So for these kind of like low depth Fs, you might have a different. It's probably, but I guess the point is that the degree will prevent you.
Exactly. So what you're saying for the functions that are kind of natively small degree, you can immediately get an extension, but the degree will not be the minimal degree. So to get the minimal degree, that's how you do it. Yeah. Good. Thanks. Any other questions? Okay. I just want to remind you, questions are great. I hope you just witness it because it's good for people, for all of you. So please ask questions. Okay. Should we dive in? Okay. So the first thing to notice is actually you should be familiar with this theorem for the case where m equals 1. So first just notice for m equals 1, this theorem is simply known as the Lagrange interpolation theorem. This is really just Lagrange. Okay, what does Lagrange interpolation theorem says? Just to recap, it says that if you have if you have an f exactly the same, I'll just write it, from h to 0, 1, then there's a unique way of extending it to f to be of degree h minus 1. Okay, so there's a unique f tilde from f to f of degree h minus 1, and moreover, I'll tell you what it is. Let me just tell you what this f tilde is. The f tilde is simply sum over all the h's in h. F of h times some polynomial chi h of x, where this polynomial is 0 on all the h elements except for on this specific one. Okay, so this polynomial where, so this is the f where chi h of x is what? Is 1, where if for every h prime in h, it's 1 if h prime is equal to h and 0 otherwise. Yes?
Shouldn't that be the inverse over there?
Shouldn't it be the inverse?
Because you want 0, the output should be 0, 1, right?
I want the output to be, yeah, so, okay, let's see. What I want that if I'm somewhere in h, so I want to say that if I'm somewhere in h prime, I want to get f of h. I want f tilde so for any h star, I want f tilde of h star to be f of h star. Yeah.
Either 0 or 1, right?
Which is either 0 or 1. Yeah? Yeah.
That's what I'm saying.
Oh, sorry.
F of h should be the inverse so that when you apply on h star, it cancels.
What do you mean f of h should be the inverse? I'm not sure. You're saying here I should have inverse?
Yeah.
Why? So,
Because x of h will give you something that's non-zero.
okay, so let me try to argue. Let's try to do this together. So if this is chi, so I first define chi of h, okay? That I'm going to define it in a second. Actually, I didn't finish defining it, but what's important to me, that on every h prime in h, it's 1 if h prime is equal to h and 0 otherwise. Suppose I defined it. Now let's see what I get here. I have f tilde of h star is sum fh chi h of h star. But this is always 0, except it's 1 when h equals h star. So it's always 0, except for when h equals h star, and when h, oh, you're saying when h equals h star, then I have f of h star. So this does extend, yeah?
Yeah.
So we're good? Okay, great. Okay, but let me just mention what is, I said this is the chi, but let me actually be explicit. So let me erase this. The chi in the Lagrange interpolation theorem, it satisfies this, but let me actually tell you exactly what it is. It's pretty simple. It's just sum over h prime in h, and then it's, I think, h prime minus x divided by h, oh, sorry, multiplication, h prime in h minus, except for h, and it's h prime minus h. Okay, so first note, this is of degree h minus 1, and when you look at it for any element, for any element h prime, it's going to be, this is going to cancel out unless you happen to be h. Oh, wait, did I do it wrong? Unless you're h and then you're 1. Good. Okay? So this is just a recap for Lagrange interpolation. Okay? Now let me tell you here, so this theorem says the same thing but for m bits, for m variables. Okay, and it turns out, you know how this was f tilde, here f tilde of z now is in f to the m, is very similar. It's also sum f of h1 up to hm. So for every point times this chi h1 hm of z. And what is this? This is 1 if z, okay, on the small hypercube, this is 1 if the z is h1 up to hm and is 0 otherwise, and it extends. So, but actually, let me be more specific. It's really where chi h1 up to hm of, let me call it, x1 up to xm is just the multiplication of chi hi xi. I goes from 1 to m. Okay, so let me move this board. Okay, don't let me erase this board, okay? We'll need it. Okay, so again, what is the low degree extension f tilde? It's similar to the univariate case. You sum over the entire hypercube, and you multiply by by the degree h minus 1 in each variable. It's just a multiplication of all of these chi-i's that were defined here. Okay? Okay, so let's see if let me try to, to prove that this works and that it's unique. Okay. So first, what do we need to argue? So we have this f tilde. Now I need to argue that it extends. So the fact, so proof. So let's first see that for every h1 star up to hm star in h to the m, let's look at f tilde of hm. What is it? It's just sum f of h1 up to hm times chi of so let's look at f tilde on any point in the hypercube. I define it by star because it's a specific point. And I just substituted, I defined this f tilde. I just substituted z because this is my z point. And now what do I have? I know that this is equal to 1 if and only if hi star is equal to hi for every I. Because this is how the chi is defined. This is just a multiplication of these chi's. Okay, so therefore, that's it. This is just f of h1 star up to hm star, because the rest of the terms cancel. Done. Yeah, so it extends. How about the degree? What's the degree of f tilde? It's just the degree of these chi's. So let's look at degree I of variable I. It's the degree I of chi of h1, hm, and which is what? It's just the degree of a single chi hi on xi, because this just factors to multiplication chi I on xi. So that's just the degree of this, which is, by what we saw there, simply h minus 1. Done. Okay, so it is indeed, it extends f, it's the degree is correct, h minus 1 in each variable. The only thing that I need to argue is that it's unique. Questions? Okay. So the uniqueness will follow from the uniqueness in the univariate case. Okay, so we already know from Lagrange interpolation theorem that in the univariate case, f tilde is unique. Now we're going to rely on that to argue that in the multivariate case, f tilde is unique. Okay? Questions? Okay, so let's do it. So uniqueness. So suppose for contradiction that it's not unique. Okay, so suppose for contradiction that it's not unique. So there exists two ways to extend that agree on the hypercube. This means that if you subtract these two, you'll get a degree h minus 1 polynomial in each variable that in the hypercube is 0. But it's not 0 because there are two different polynomials. So it means, suppose for contradiction, let me just erase this because it's in my way. Suppose for contradiction that there exists like a g from f to the m to f, non-zero, but g on the hypercube is 0. That's the contradiction. End of degree. H minus 1 in each variable. Yes, that's a contradiction. We say, suppose there exist two polynomials that agree on the hypercube of this degree. We're going to subtract them. We're going to get a single polynomial that's just 0 on the hypercube because the two agreed. But it's not 0 because they were not the same polynomial. Okay. What does it mean, non-zero? Okay, exists. Okay, what does this mean of degree n minus 1 in each variable? Okay, the fact that it's non-zero means that there exists some t1 up to tm in f to the m, such that g and t1 up to tm is not 0. Yeah, so we're starting with saying, suppose we have g, it's not 0, but it's 0 on the hypercube. I'm going to argue, no, it can't be. I'm going to find an element in the hypercube for which it's not 0. Okay, how do I do that? What I'm going to do, I'm going to kind of go into the hypercube coordinate by coordinate, kind of by induction. Okay, and here's what I'm going to do. I'm going to say, okay, let's look at G empty T2 up to Tm. This is non-zero because on T1 it's not 0. So this is non-zero of degree h minus 1. But from the Lagrange interpolation theorem, it says that if it's not 0, there must exist h in small h and h for which it's not 0. Because if it was 0 on all h, there's a unique way to extend, the 0 polynomial. So because the uniqueness of the Lagrange, it means that, so from Lagrange theorem, this is just univariate. It means that there must exist h1 such that g of h1 t2 up to tm is non-zero. Again, why? So the t's are fixed. This is a univariate polynomial. If it was 0 on h, then you could extend it to all zeros. But there's another way to extend, because the g is not all zeros. That would be a contradiction. So therefore, there must exist h1 such that this is 0. And now we're going to slowly continue in this manner. Okay, now let's look at g h1 t3 up to tm. Okay, so h1 is fixed in the small cube. These are fixed in f. It's non-zero because on T2, it's not 0. That's what we established. So this is non-zero of degree h minus 1. And therefore, somewhere in the small hypercube, and somewhere on h, it should be non-zero from Lagrange interpolation theorem. So therefore, from Lagrange interpolation theorem, there exists h2 such that g h1 h2 t3 up to tm is non-zero. And you just continue one by one until you get that there exists g h1 h2 up to hm. That's non-zero, and that's a contradiction, because we assumed it is 0 everywhere on the small hypercube. Yeah? Okay, so in the notes I have like the reduction, there's a proof that's kind of by induction, very formal, but I think this is good enough for class, otherwise it's going to be a bit boring. Questions? Yes?
Can you also just use a counting argument? Like, you can just count how many polynomials of degree h minus 1 there are, because like, you break it up into like all the terms, and that's just equal to the number of functions. Okay, good. So you're saying maybe you can also prove it using just a counting argument. Say if there's too many, then like you'll have too many polynomials, and that's a contradiction because the number of polynomials, like the number of coefficients, probably you can do something like that as well. Yeah.
Can I try to make the case for the arithmetized?
Yes, please. Good.
So the arithmetization, right? You can compute it on any element in f to the m.
And if, yeah.
Easily, I guess, without looking at the truth table of the original function.
Good. Oh.
Right? You just compute it.
Yeah.
To compute f on any point, you need to look at the entire truth table.
Good. Very good. Okay. So what you're saying is, look, once you force me, once you don't, I said, look at me, I don't assume anything about F. You assume low degree, look at me, I assume nothing, and look what I get. Now you're saying, well, you assume nothing, but you don't get that much either because this F tilde is so inefficient. Note, to compute this F tilde, where is it? It takes time h to the m. You need to sum over all the hypercube. So computing F tilde is really inefficient, whereas your F tilde is so efficient and nice, 100%. Yes, you're right. I'll give it to you, Vinod, yeah. No, but this will be useful in settings that the arithmetized version will not be. But that's a good point. Thanks.
Is there like an easy way to like bound the number of monomials? Like, is there some like unique F that has like at most so many monomials?
Okay, so so the question is, can we bound? Essentially asking, well, can we make this F tilde a little more efficient, maybe, kind of? So in general, we cannot, because in general, it depends what you want to assume about the F. So I'm saying I don't want to make any assumptions about the F. And as you will see, it's not just because I want to just be as general as possible for the sake of generality. Actually, in the way we use it, it really has no structure. The F we use is kind of very arbitrary. So we can't assume that it comes from a low degree, whatever, nothing. And in that case, if you want to allow any F, then you have to have all the monomials, because there's, just by a counting argument, the number of F's is like, all the possible h to the m bits. So you have to have that many monomials. Otherwise, where would you store that information? So in general, you can't do with less monomials. However, in many cases, you can do. And actually, even we'll use it, the fact that in some cases you can do with less monomials. So we'll see that. But that's great point. Any other questions? So let me just tell you, this is a very good theorem to stop and ask questions, because it's really, we'll get back to this so much. And even if not in this class, you'll see it and it will come at you. It's a really, really important and fundamental theorem. Okay, so I guess next I'm going to try to convince you why it is such an important and fundamental theorem. And I'm going to start with just kind of looking back at the example of doubly efficient interactive proofs for counting triangles, just as a motivating example. We'll do it quick, and then we'll go into kind of, I think, the more kind of interesting and general way of using this low degree extension together with a sum check to get doubly efficient proofs for any low depth computation. So kind of arbitrary computations. So we'll see that next. But let's first kind of, as a warm up, look at the example for counting triangles. Why is this low degree extension with sum check? How can we use these together to count triangles in a graph? So now note, what's the goal? We have a graph. I want to know how many triangles there are in the graph. Now, it's not that hard. It takes time n to the third. I go over every 3 pairs of vertices and check if there's a triangle. So I have an n to the n cubed algorithm. But let's say the verifier can't run in time n cubed. The poor guy, he gets the graph, so size n squared. All he can do is run time n squared, essentially, a polylog with some polylog overhead, but only n squared. So he can't count. So now what does he do? He needs help. Okay, now I'll show you how the prover can help him in a way that now, yes, he only needs to run in time n squared, or O tilde of n squared. Okay, so let's look at that example. So let me erase this. So here's an example where this is useful. We're given a graph. And the goal, we want a protocol, a proof where the prover will convince the verifier that the number of triangles in G is, let's say, some number beta. I want to prove for this fact. How will I prove? So I'm going to prove to you. You guys are time O of n squared. You can only read the graph. I'm going to help you prove to you that the number of triangles is exactly beta while you just run time n squared. How do I do that? Let's look at the function f from, so suppose v is n, okay? So I look at the function from 0, 1 to log n to 0, 1. And this just tells me whether, so 0, 1, so it's like 0, 1 to the log, you can think of this as being kind of n by n. So it takes log n bits that describe one vertex, log n bits that describe another vertex, and it outputs 1 if and only if there's an edge. Okay, so you can think of each, so f takes 2 vertices I and j, and outputs 1 if there's an edge, and 0 otherwise. So f is just the adjacency matrix. The adjacent matrix is, n squared bits. This is n squared, I just put it and define it this way. Okay, so again, f takes 2 vertices, it outputs 1 if there's an edge between these vertices. Okay, now, so what do we need? So, okay, now what do we know? We know that this f has a low degree extension. So this is of a degree, essentially this is multilinear, because I started with 0, 1. So this is, so f tilde is multilinear. So degree 1 in each variable. Now, why am I looking at these adjacency matrix? What do I want? What do I want to prove? How does this relate to the number of triangles? So the number of triangles, we started discussing this last time, is just the sum over all kind of triangles, I, J, K, all kind of 3 nodes, I, J, K, and V. And it's a triangle if what? If f, I, J is 1, and f, J, K is 1, and f, I, K is 1. So I want to know how many triplets is this thing 1. If an edge is missing in one of them, then this is going to be 0, because I multiplied. So I want to know how many of them do I have 1. Okay, and that's almost the number of triangle, except that I need to divide by 6, because I counted each triangle, each 3 vertices, all the permutations. So that's what the prover wants to prove to the verifier. Okay, so I said v, but let me call it 0, 1 to the n, to the log n, which is the same. Now, I'm done. Why am I done? Because I'm saying, you know what? So how do I prove this? I'm going to use the sum check. But you're saying, wait, but this is not a polynomial. No worries. Here you go. Now it's a polynomial. Now I didn't change anything because it's only over the small cube. So the fact that I extended doesn't change the sum. Okay, because of the extension. So the prover needs to prove that the sum of this polynomial, so before it was multilinear, now it's degree 2, because each variable, we multiply 3 polynomials, each one appears in 2. Fine. Degree 2 in each variable. And we need to prove that the sum is beta. This is exactly what sum check is for, precisely. Okay, and note, what does the prover, so what are we going to do? We're going to do sum check protocol. What is the runtime of the verifier in the sum check protocol? So they interact, we do, every time you get rid of one variable, one by one by one. At the end, the verifier needs to compute f tilde, the final polynomial, which in our case is this entire polynomial, on a single point in the extension. Namely, he needs to compute f tilde on a random point in f, in, I guess, f squared, 3 times. But that he can do very, very easily. Or what do you mean, in time n squared. Because what is f tilde? F tilde, I mean, as Vinod said, you need to enumerate over all the small cube, blah, 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 it's a lot. But here the small cube is n squared. So it really takes time n squared so order of n to it. He needs to do 3 times. He needs to compute this, but this is polylog. So, by the way, throughout this, I mentioned it last time, but I'll mention again, throughout this course, the polylog factors, I'm not even, these are all like, you can put things like in tildes. I'm kind of I don't want to pay attention too much to polylog factors. Okay? So really the runtime of the verifier is just n squared. The communication complexity is nothing. M, number of variables, is order log n. D, the degree is constant. Log f, well, don't take f to be too long, too big. Take f, so that log f is small. And note, even the prover doesn't run in too long. What's the runtime of the prover? It's in the sum check protocol. It's m, the number of variables, log n, times h to the m. Now, h to the m seems big, but again, it's n squared, times the time it takes to compute f once, which is, again, n squared. So he's polynomial. And now the verifier runs in time squared. OK, so that's just kind of to illustrate. Yeah. Yeah, right, and he is. He's actually he's n to the 4th in this example because he runs. He needs to compute this. Okay, let's see. He's more actually. He needs to compute this thing. So he needs to do it for every ijk in, right? So, and it's yeah. He needs to do not just to compute, to do the entire sum check. So in the sum check, he needs to kind of h to the m, which is m here is going to be 3 log n. So in this, so it's like already n cubed, and then he needs to compute t of f, like the polynomial, which is n squared. So he's n to the 5th. Because computing this once is n squared without the sum. But he also needs to run over all the sum, and then also log factors. Yeah, he's running more. But it's considered still doubly efficient because it's still polynomial overhead. Yeah?
There's no way to get it down to like n to the omega or something? But through runtime, since that's the actual runtime.
Yeah, even n cubed, you're saying. Yeah, currently, it's a good, so, okay, n cubed, you can get it using recent kind of really nice works. With just optimizing a little bit, that's the work of Dan Sung and friends. They get it linear time. So they can get an n cubed. I don't know how to, but it may be that for this specific protocol it's possible. Actually, I don't know. It's a good question. But let me actually, before you get too excited about it, so, yeah. Yeah.
So the number of rounds is log n, right?
The number of rounds is log n.
So to ask, like, you actually get like a 2 message.
Great, great. Question can have 2 message. So when I finished, where's Gabe? Oh, hi. So you came to me last time, right? So when I started talking about this last lecture, Gabe came to me, rightly so, and said, well, we just started talking about it, right? And he's like, well, okay, but you can do it so much easier. And it's true. This was kind of as an example to show. But actually, since you asked the question, also, actually, there's a very much simpler protocol that Gabe noticed. So let me just write it here. The idea is that the prover will only send 2 matrices over. So it's a big communication complexity. Here the communication complexity is polylog. But if we just care about verifier runtime and we don't care about the communication complexity, then the prover can just send the verifier. So think of, let A be the adjacency matrix. Let me now, instead of F, write it in the more classical notation of a matrix A, the adjacency matrix, where there's an edge if there's a 1 if and only if there's an edge and 0 otherwise. The prover will send the matrix A2 is A squared. A, he can also send A, but the verifier knows A. And A3, which is A cubed. Now, the number of triangles is just the trace of A cubed. So it's very easy to compute. You just compute. Now, how do you know that this is A squared and this is A cubed? Well, we saw last time a randomized protocol for checking equality between matrices via kind of this Reed-Solomon kind of decoding idea. So you do that. So There you go.
That's really, really nice.
Yeah.
I'm not happy still.
Well, but then blame Gabe, of course.
The communication complexity.
Exactly. You're right.
You can get the best of both worlds, right?
Okay. You can get, okay. I need to, so you know, there's a really beautiful work of RRR, and they get constant round complexity. And so using their protocol, probably you can get very good, but I need to think about the parameters. I think you can get in constant round, like, probably, like, really good parameters. But I need to think about the details. Yeah. Okay. So this was just a motivating example to show you that you can take something also with no structure whatsoever, like adjacency matrix. It's no structure, it's arbitrary. But using the technique of a low-degree extension, you can kind of add structure to it, and then you can a cheating prover. And so you want some encoding, kind of. You want to say if he cheats somewhere, he has to cheat everywhere, and kind of that. So this idea of kind of having, in some sense, you want kind of a, if you want the proof to, you want to, it's very natural that kind of some encoding comes into proof systems. And we'll see that next when we look at the GKR protocol for low-depth computation. Okay, so that's coming next. Now, before I start this protocol, I have a question for you. So last time, this is a long class. It's a 3-hour class. It's tiring. So, and it's technical, which is even more tiring. So now I want to ask you two options. Option one, we'll take 2 breaks. One after 1 hour, one after the second hour. It will give you kind of, or we take one in the middle, which is maybe a little longer. How many people are for like 2 kind of short breaks to decompose? Let's take a break now for 5 minutes, and then we'll do GKR. Okay, so far when the applications we saw, for the sum check and even if you want the low degree extension, we're both kind of counting. You know, we said, okay, let's count the sharp sat. Let's count the number of triangles. So you may think, okay, well, sum check is about counting. So yeah, I can see how you can do counting problems by either they're already kind of low degree and you just apply sum check automatically, or they're not low degree and then you do low degree extension and now you have the sum check. Okay, so maybe you can do kind of counting things, but that's it. So now what I want to show you next is that no, actually, you can do a ton with that. So just the low degree extension and sum check together, that's all you need. And what I'm going to show you now is how to do a doubly efficient interactive proof for all low-depth circuits. So let me explain. So suppose you have here some circuit, C. It's really, really big, but it's shallow. Okay, so think of this circuit, size S, which is really big. The depth is D, which is very small. Okay? Now what I'm going to show you is a doubly efficient interactive proof where the verifier runs in time only D, or linear in D, or D and polylog in S. And the prover, of course, he needs to compute the circuit. He runs in time S. He has to run the computation, and only poly overhead, so poly of S. Okay, so I'm going to show you a doubly efficient interactive proof for any bounded depth. Yes?
And just to clarify here, circuit size is just number of gates?
Good. The circuit size is just number of gates, yeah. Yeah. Now, note, this already seems like weird because, okay, so the prover, I said the goal is the prover is going to convince the verifier that, let's say, so the goal is to convince the verifier that C of X equals, let's say, 1. Think of C as any Boolean circuit of small depth. So now, and the verifier should be very efficient. But now you're saying just reading C is not efficient. If you have an arbitrary circuit, just reading the circuit is not efficient. You're right. So for this to be meaningful, C needs to have a succinct representation. So it needs to be kind of a uniform circuit that you can specify it succinctly. And indeed, we will assume that C is what's called log space uniform, which essentially means that there's a log space machine, a log S space machine, that uniform Turing machine that generates this circuit. But actually, for now, don't think about it. Just suppose it's just kind of there's some uniform condition. Okay, so the verifier has succinct representation of the C, because it will only come much, much later when you'll see this kind of, you'll need to deal with this issue. Okay. So the goal is for the prover to prove to the verifier that C of x equals 1. And the idea, the way we're going to do this essentially is, the high-level idea is we're going to kind of, so the prover, so I want to kind of catch the prover if he's cheating. How am I going to catch him? I want to make sure he's correct. So the prover comes to me and says, look, C of x equals 1. The value here is 1. I want to reduce the claim on the output value to a claim about something in one layer below. And then by like a small subprotocol. And then I want to reduce the claim about something about kind of layer below to layer below and layer below and layer below and layer below and so on until I get a claim about the input which the verifier can compute on his own. That's kind of the idea. So for this, the first thing we assume, and this is without lots of generality, that C is layered. What do I mean by layered? There's an output gate. There's kind of, that's, let's call it layer 0. And then you go to gate, and then there's kind of wires to one layer below. We'll call it layer 1. And then there are gates to one layer below. We'll call it layer 2. So it's not, there's no kind of long gates that go from the input straight to kind of, it's really layer by layer. Okay, so that's the first assumption. So we can talk about layers. So what it means is that gate in layer I is connected only to gates in layer I plus 1, where we think of I equals 0 as output. And I equal D is input layer. Okay, so this is just for the sake of simplicity. You can always kind of add dummy gates to make sure that each gate is only connected to one layer below. If before it was connected to someone closer to the input, you just add dummy gates to kind of go up, up, up. Okay? So again, let me just make sure everyone's on board. But by layer, when I say a gate is in layer I, essentially what I mean, the depth from there to the input, the number, the path, the length of the path is I. So any gate that is kind of I away from the input, it's connected to gates that are only I minus 1 away from the input. Okay, so we assume that's an assumption I'm going to make. And the way I can realize it is by just, if this original circuit was not in this way, I'm just going to add dummy gates in the middle. So if a circuit at layer 3 was connected immediately to the input, I'm going to just copy the input in 1, 2, and then I'm going to kind of connect it. So things are going to be layered. Questions about this assumption? Okay, so now the circuit is layered. And now what I want to do, I want to reduce. So now I'm going to have an interactive protocol. So the idea in GKR is to have an interactive protocol that consists of D subprotocol and each subprotocol essentially reduces a claim about some layer I to a claim about layer I plus 1. So a claim about the layer that's one closer to the input. Okay, so these are kind of how these subprotocols will go. I'm going to explain the GKR protocol formally, but this is just intuition. Okay, so let me take this actually. So the first thing is, okay, so here's kind of the idea. So again, this is not the protocol. I'm kind of giving an intuition of kind of what, helping you kind of understand where I'm going to go. So we want to prove a cheating prover. Suppose he's cheating. He's trying to argue that C of x equals 1. But think of it, it's not. We want to catch him. How do we catch him? If he's cheating, how do we catch him? So one idea is to say, well, if he's cheating here, he must. So let's say this is an AND gate. Suppose it's 0. But he's claiming it's 1. So it means that I'm going to ask him, you know what? It can't be, if I tell him, give me both of these, he also must be cheating. So I'm going to tell him, you know what, really, this is 1? So in that case, you claim that both of these are 1. He's like, yeah. Or if it was an OR, I'm saying, oh, this is 1, so you claim that one of them is an R, right? He's like, yeah. So, but in reality, they're both 0. So now what I can say, you know what, okay, fine. I'm going to choose one of them at random. And really, okay. Tell me that this is a 1. So I'm going to, he's, by cheating, one of these has to be a cheat. So I'm going to prove to him, really, so show me this. And then I'll go down, show me, and at the end, he's stuck because it's an input. So this is a very easy approach. The problem with this approach, I lose probability half in each layer. Okay, because suppose if it's an AND, let's say it's a 0, then he tells me, oh, one of them is 0s. But in reality, I know they're both 1. So I'm going to tell him, oh, really? Both of them are 0? Fine. I'll choose one of them. Okay, show me this is 0. But maybe this really was the 0, 1. And then he'll, of course, cheat. So I'm like, finger crossed, this was actually a 1. But only with probability half. And then, so that idea works very well. It's just the soundness is 1 over 2 to the d. So that's not good, because 1 over 2 to the d is like the size of the circuit. I need to, that sucks. Okay, no good. So what do we do? So here's the basic idea. The idea is, you know what? Don't ask per gate. That's not a good idea. Let's ask something about kind of an encoding of the entire layer. So instead, I'm going to ask them, give me something kind of about the low degree extension of this layer. So I'm not going to ask them, reduce it, tell me this. No, tell me something about this. And then I'm going to argue, if he cheated here, he must also cheat here with very high probability. And now, and again, if he cheat here, I'm going to argue that he must cheat here with very high probability, and so on and so forth. But now, that's kind of the high-level idea. But now you can say, whoa, this is a bit confusing. Before, when I said, oh, if he cheated here, I'm going to ask him cheat on one of these, it's very easy for me to check. If you say this is 0 and it's an AND, you're claiming that one of this is 0. But I know one of this is 1. So it's very easy to argue. How do I go? So I can just say, okay, prove to me that, this is a 0. Or prove, that's easy. How do I go from arguing about the low degree extension of an element of a layer to low degree extension of another layer? What do I ask you even? And it turns out that what I do here is really low degree extension and sum check. So I go from here to here, it's just a sum check. So that's what we're going to see. Okay? That's kind of the high-level idea. Any questions? Let me just make sure I didn't forget to say something. Okay, good.
What's the goal for the verifier runtime?
Good, okay. What we're going to get, okay. Goal, as efficient as possible. What we get is the verifier's runtime and the communication complexity will be like D, the depth, times polylog, the circuit size. And the reason we pay this depth is because in the protocol, we're going to run D subprotocols. We're going to kind of go from a claim on layer I to another claim of layer I minus, and each kind of reduction in the layers is going to be kind of a subject protocol, which will consist of log S rounds, or log S. It's the M, the variable is going to be log S. So eventually, the runtime of the verifier will be something like the depth times log the circuit size, and the prover is going to run time Pauline the circuit size. But we'll go over all these parameters once we see the protocol. But that's what you should. That's kind of the theorem that we'll write when we get there. Great, thanks. Any other questions? Yes.
So the verifier isn't able to see the whole circuit.
Right.
Like, how does the verifier get access
Good.
to the circuit?
Good. So the verifier, as I said, he can't even see the entire circuit. All he has is like some uniform Turing machine that generates the circuit. So that's a very good question. How does he? We'll see. It's complicated. The answer is it's complicated, but we'll see. We'll see as we go along. He'll use his kind of uniform access to help him out. It's really unclear how at this point. Great. Okay. So what do we do? So first thing is, so step one, this is just again for simplicity, arithmetize the circuit. Remember last time we had arithmetization? So arithmetize, all I mean here is convert an OR to kind of, convert an AND to multiplication, convert an OR into the sum minus multiplication. Just convert the OR and an OR gate into addition and multiplication gate. Okay, so step one, arithmetize C so that it consists of only add and mult gates. Now you write at this point, the verifier doesn't even know. So we'll talk about how the verifier has access to these things later. Okay, but like the prover, what he does at least. Okay, the prover first arithmetizes this circuit. So it's add, and now everything, all the gates are multiplication gates and AND gates and addition gates. Good. Now what he does, so he wants to, I want to convince you that C of X, we said 1, so I'll make it 1. What do I do? I'm the prover. I take my input X. I compute the values of all the gates in the circuit. Okay, so what does the prover do? First, compute the values of all the gates of C. Okay, so now the prover computed all these bits, which are the values of the gates. Note, this is still over just, it's Boolean. It's over kind of GF2. Yeah, it's everything is 0, 1. Okay. Next thing I do is the prover does, he computes the low degree extension of each layer. Okay? So what are the parameters? How do we do it? There's many ways to do it. Let's think of, let me add actually another assumption just for simplicity. Let's assume that the number of gates in each layer is exactly S, like the size of the circuit. I'm just assuming that, so I don't need to now have different S's. It's just going to be annoying. Why can I assume that the number of gates in each layer is exactly S? Just add dummy gates that are just 0. Nobody's going to look at them. Okay, I'm just it'll just make my notations easy. Okay, so now if there's less, just add zeros. 0, 0, 0, 0. So now it's like this kind of circuit by just adding zeros everywhere. Okay, good. Now, what does the prover do? He thinks, so now each layer consists of S values. That's the assumption. It's that we added demi-gates. So now we have S values per layer. Okay, many of them can be 0 if the layer was short, but there's S values. So let's write these values this is for layer I. Let's write these values in a hypercube. Okay, so let's write these values as kind of a function from h to the m to 0, 1, where h to the m is exactly s. So we said each layer has s elements. Write them in some hypercube where the size of the hypercube is exactly s, so you can write all these elements in the hypercube in some order that makes sense to you. Okay? So if you want to take h to be 0, 1, just take the binary representation of like each gate. The gates are numbered, and vi of this number is the value of this gate in layer I. Okay, so each gate in layer I has kind of a number, which is a number in h to the m, and this is the value of the gate. Okay, now what is h and what is m? I said, you know, it needs to be of size h to the m. H to the m needs to be s, so I have place to write all the values of the layers. But which h and which m do I choose? And now actually there's freedom. So in many times it's easier to think like we're used to binary because we're kind of computers. So it's comfortable to think of h as being 0, 1 and m to be log s. You can think of it this way, that's fine. However, later, like probably Rachel will tell you about it, it'll be convenient actually. Rachel's like, oh no, what did I sign up for? It's like, I'm not going to tell you. It'll be convenient actually to take the parameters which are h being log s and m being log s. Okay, fine. I tried to put in the same, didn't work. M being log s over log s. So it'll be convenient to think of these parameters. So first just note that log s to the power of m, which is log s over log s, is just, log s is just 2 to the log s times this thing. These two cancels, and therefore you get indeed s. So I'm just saying these parameters, indeed, if you take h to the power of m, you get s back. Okay, because h log s to the power of m log s over log s is like 2 to the log s, and then the 2 log s cancels, and you get 2 to the log s, which is s. So this is good. Okay, you get what you want. But you can be like, why am I taking this setting of parameters? And you also may be kind of annoyed, like, why are we talking so much about parameters? This is kind of boring, and I agree. However, this is important because these parameters are used a lot and for a good reason. So let me tell you why these parameters, why am I spending your time on these parameters, this specific choice? And the reason is that later, when we'll take extension, remember we take extension over a field. We'll take a big field. Now the field, if you remember the subject protocol, the soundness you get is like m times d, the number of variables times the degree over f. So f needs to be of size at least m times d. Okay, so it will need to be at least like this m, which is, if you take like binary, like 0, 1, it'll need to be at least log s, which is the m. Or here, you know, the number of variables is not constant usually. And it'll need to be bigger than the number of variables. And now the problem is, if you take, what's very desirable in later applications, in particular for PCP applications, which we'll talk about, it's really beautiful. For those who haven't heard of what PCPs are, we'll learn about it. It's really, really nice. But for these applications, what you want is that f, the size of the extension you take, is poly in H. And now if you take H to be 0, 1, which is what, like binary, which is what we all like, then the field becomes constant size. Because it needs to be for applications, like to get the PCP, you need f. If f is bigger, you'll get like a super polynomial object. So to get kind of for later applications, it's important that the field is not too much bigger than h, that it's polynomially related to h. And then if you take h to be small, like constant, like 0, 1, then f is a constant, and then you don't get soundness, because m is not a constant. To get soundness bigger than 1, you've got nothing. So this is, if you didn't follow, it doesn't matter. You will see it when we talk about PCP. But this is just to tell you why I'm choosing these weird parameters as opposed to 0, 1. The point is that later we'll need these parameters when we'll talk about PCP. And so that's why we're using them now.
Okay, are you saying that for GKR itself?
GKR itself you don't need.
Because you're never writing down the entire...
Exactly. Because, exactly. Because in GKR it's interactive, you're never writing down the entire thing. For GKR itself, you can take h to be 0, 1, and you can take f to be big, and like the kind of parameters you want. I was actually debating if to teach it with 0, 1, and then to change all the parameters, or in many, like if you look at Justin Taylor's notes that are in the website, gave the exact chapter, then he uses 0, 1. Because it's easier, and you know. But since I'm going to change the parameters anyway, I thought I'll just start with them. And I think it's good to get accustomed to these type of parameters because they show up a lot. Okay, so this was just kind of, if you didn't follow exact choice, don't worry about it. It turns out this is the choice I want. And why, you'll learn about it when we talk about PCPs. But if you want to think about h as 0, 1, and m as log s, you can do so all the lecture. Everything I say makes sense in that parameters, and you know you'll understand everything with these parameters as well for today. Okay. So good. So now what does the prover? What will the prover do? The prover will. So he has for every layer, he has the values of the gates. He computes the values of the gates of that layer, which is, you can think about it as for each layer I, the prover computes vi, which is the value of all the gates in layer I. So we can think of the gates as kind of going from h to the m to 0, 1. Each gate has a label in h to the m, because it's kind of the same, it's isomorphic to s. So each gate has a label here, and this is just the value of the gate on input x. Okay, so this is the proof. There's no protocol yet. I'm just telling you what the prover computes before the protocol begins. Okay? And now the prover can compute the low degree extension. Okay, so this, let me actually be careful with room. So I'll write it here. This is nothing but the low degree extension of vi. Okay, now we're in business. Once the prover computed this, then we're in good shape. So now let's go back to the protocol. What do they do? So as we said, the goal is to reduce. So remember, the first thing the prover gave the verifier, you can think of the protocol started with V0, which is the output layer, and one element, let me call it Z0 because we're going to call them Z, and Z0 in, h to the m in this time, which is kind of just, actually the output layer has just one gate, right? It's 0 or 1. We added a bunch of zeros to it because we want dummy gates to assume that it's kind of size S. But there's one gate. This is, let's call this gate Z0. And he's arguing on Z0, there's a certain value, V0. In our case, we said it's 1. So he comes with an argument, right? He tells us, look, if you look at the output layer, this is the output layer. If you look at the output layer, and the relevant gate, and the actual single not dummy gate, I claim the output is V0, namely, let's say 1. Now I say, why would I trust you? And he said, okay, let me help you. Here. I can always add tilde, okay. So now, let's see. What is V0 tilde on any element Z? What is this value? Remember, this is the output, yeah? So it is what? And what I'm saying here is actually general. Even let's think of I, like layer I. Okay, you can think of layer 0 if you want, but in any layer, take any layer, and take any zi, even in the extension, in f to the m. Here, it happened to be that the z0 was actually kind of not in the extension even, because we started with a certain gate. But let's kind of think of it more broadly, because later we'll be in the extension. So I have the prover claims that this is vi. We start with I equals 0. I don't know if that's true. I want to reduce it to a claim about layer I plus 1, one layer down. How do I do that? What is vi tilde and zi? Zi in general is in the extension. In this case, it's not, but in general, it's in the extension. So first thing, let me move zi not to the extension. So let's remember, what is vi tilde? Vi tilde is sum. A vi, that's kind of the original vi, on h, let me make sure I'm consistent with my notation so I won't confuse myself. Okay, on point P in h to the m times this chi P of zi. I just kind of, right? So what is the low degree extension of V? It's the VI on every point, not in the extension, in the cube, in h to the m, times this kind of chi function, which was this, I erased it, but it's the, this multiplication, each one of them was this degree h minus 1 function. Okay. But what is VI? VI, we can easily relate it to the layer 1 below. VI is either an add gate or a multiplication gate. If it's an add gate, it's an add of 2 elements below, and if it's a multiplication of 2 elements below. So now, to connect it to the layer below, and this goes to the question of what does the verifier know, whether it doesn't know. What I'm going to use is the circuit so the circuit is associated for every I with an add function and a multiplication function. And this function goes from 0, 1 to the, 3 log s to 0, 1. And it just says whether you take a gate in layer I and 2 gates in layer I plus 1, and it checks whether there's an add there. Okay, so it takes kind of I, j, and k, and it says 1 if and only if gate I, I is taken. What notation did I use? It takes a gate P, W1 and W2 in S, one of the gates, and it outputs 1 if and only if gate P in layer I is add of gates W1 and W2 in layer I plus 1, and 0 otherwise. I start with 0 and I go down to D. Yeah, and 0 otherwise. Okay, so just check if there's an AND there, if there's an add there. And mult is exactly the same. Mult checks if there's a multiplication gate. Okay, so mult also takes P, a point P in layer I, 2 points in layer I plus 1, and it outputs 1 if and only if this gate P in layer I is actually a mult gate, a multiplication gate, and it connects to gates W1, W2 in layer I plus 1. Okay? Okay, so what is this? Now we can say this is nothing but sum of P. Let's sum over all the possible W1 and W2, all the gates in the layer below, and see, maybe it adds. So if there's add, if add I, P, W1, W2, if that's 1, then you have VI. Then VP is just VI W1 plus VIW2. If P is an add gate, if it's not an add gate, you'll get a 0. So you're not adding anything. If it happens to be an add gate, then what the value of this gate is just the sum of the values of the gates below. If P is not an add gate, all this is 0. I didn't do anything because I multiplied by add, which is 0. Okay. Plus sum plus let me just open plus mult I P W1 W2. If it's a multiplication gate, and let's say it's connected to W1 W2, I'm still in the sum. Then what do I do? Then what's the value of VIP? I mean VI in point P.
VI of W1 times
Exactly. VI on point W1 times, because it's a multiplication gate. VI in W2. Sorry, plus 1. Thank you, thank you. Yes, great. Good. And all of this times this polynomial chi P of Zi. Good. Okay. So now, where are we? We want to prove something about layer I, right? But we managed to write it as sum of elements in layer I plus 1. That's great. That's really what we wanted. We went one layer down. Okay, but so, okay, well, and note, this is really similar to a sum check. What do we have here? We want to prove that VI, so I want to tell the prover, prove to me that instead of, he claims VI is this value. I'm like, I don't know what this value is. Prove to me that VI is equal to the sum. So prove to me that VI is equal to something about the layer below. How does he prove that something is equal to this sum? Sum check, right? Okay, so do the sum check protocol. And now you're saying, wait, but where's the polynomials? No problem. Everything's over h to the m. Look at the extensions. This is already polynomial. We don't care about that's good. Look at the extensions. Okay, we have a low degree extension up here. Any polynomial can be extended. Look at the extension. Okay. So now we want to argue that VI equals the sum. This entire thing, I argue, is a low degree polynomial. Why is this a low degree polynomial? Let's see. First of all, it's a polynomial over h to the 3m, because m here and 2 w's here. So we're talking about 3m variables. But m is small. This is good. M is log s over log s. So that's good. What about here? So let's first look at the degree. The degree of these things, it's the low degree extension. It's h minus 1 of each one. Okay, because I'm really taking each one is h. Each add, everything is kind of, add is even better because we did 0, 1. So add is even better. You could do, sorry. Now, can I take it back? I also want to do add in h. Everything is in, I made a mistake, I put in 0, 1, but I need to be consistent. If I'm in h, I'm in h. So h to the, everything is in h. So everything here is degree h minus 1. So good, so it's more than h minus 1 because I have your multiplication. W1 appears here, W1 appears here. So it's going to be degree 2h minus 1. Fine, but h minus 1 is small. It's like log. So 2 logs. So the degree is small, the number of variables is small. Perfect. Just do sum check. So now you're asking, what is the GKR protocol? Sum check. That's it. Okay, you start with V0. You tell them do some check, convert it to convert this claim about the output, which the verifier has no idea. It's so far away from him. He doesn't know what. He said, let's do the sum check protocol to reduce this claim to a claim about this thing, essentially. But now this is very confusing, because what happens when we do the sum check protocol? When we do the sum check protocol, we reduce. If you remember, let's look for a second at the sum check here. We want to prove that the sum of something, there it's a huge thing, add v plus multiplication of v, all this craziness, whatever, low degree is equal to beta, is equal to something, in that case v0. We run the sum check protocol. At the end, the verifier needs to compute, to check. In the sum check protocol, we assumed that the verifier has oracle access to the polynomial. Okay, but essentially, he needs to compute this function, the polynomial, on some point. Now, maybe he has oracle access at that point, great. But maybe, okay, but there's no oracles in GKR. So what do we do now? But here's an important observation that we'll use. Note, yes, the prover needs, the verifier, when he verifies the sum check, he needs to compute the polynomial on a single point. But this point, T1 of the Tm, is a random point that's chosen by the verifier. Okay, when you look at what is the sum check protocol, the verifier chooses a random T1. He gets a polynomial, and then chooses a random T2, and so on and so forth. At the end, he needs to evaluate f on T1 up to Tm that he chose. Okay, we will use this. Okay, so now let's see. What happened here? After we did this sum check, the poor verifier needs to compute. Let me again make sure I'm consistent with my notation. Good. The verifier now so he does the sum check. Let's denote kind of the randomness that he used in the sum check by a. So we started with I. Let's say that when we reached here, let's say he needs to compute a add tilde on z I plus 1, because we moved to layer I plus 1, 0, z I plus 1, 1, z I plus 1, 2, times v I plus 1, and another end, so that was 1. So z, I don't like this notation, sorry. Let me change it. It's more cumbersome on the board than in the, okay. Let me call z0, z1, z2. So suppose they do a sum check protocol. In the sum check, it's on 3m variables. So suppose, let's denote the randomness used by the verifier in the sum check protocol by z0, z1, z2. Each of them is in f to the m. So now, the verifier needs to compute this function on the point z0, z1, z2. What is this function on this point? It's add times vi plus 1 tilde on z1 plus vi plus 1 tilde on z2 plus mult z0, z1, z2 times vi plus 1 z1 tilde times vi plus 1 z2 tilde, and then all this times this this chi. I'll put it here. Chi p of z of oh, oops. Sorry, I messed this notation. This is the zi. Okay. Sorry. Okay, zi is the original point. Yeah, that we started with. We started a claim about vi equals vi tilde of zi. Zi is a fixed point that we started with. The randomness of the verifier in the subject protocol, I denote by z0, z1, z2. These are chosen by the verifier. Yes, Vinod.
So E should be
B. Yeah, but yeah, exactly. But I'm in layer I. You're right. In layer 0, it's just Z0.
No. The B, right? The B, you replaced it with Z0 in this notation.
Oh, I replaced.
Correctly, right? So B is Z0, W1 is C1, right?
Yes. Oh, yes.
It's kind of like the renaming.
Yes. The rename. You're right. Yes. Z. Z0. Yes. You're right. And this is still a low degree polynomial in Z0. Good point. It's sitting. Yeah. Maybe I erased it. But this. No. But I didn't write this.
You did
Below here. No, but I need to write. It's like this is x I minus I think yes. So it's oh, maybe I need to take extension of this. Sorry, 1 second. This is hold on. Sorry, maybe I missed this. Let me think, because I missed in the notes. So hold on. So here the point is H. I think I need to take extension of this too, because the point here, H, this is not a polynomial in H. Okay, so let's do that carefully. Sorry, I missed that. So chi is a low degree polynomial, but it's a low degree polynomial in X. It's not a low degree polynomial in this H. Okay, H here is like in the denominator. So it's not a low degree polynomial in H. Sadly. But you can extend, so it's okay. Don't worry. So it's not a low degree polynomial. However, it is in, all we care about is if we think of it as a function of Z0 of P, then we just extend. We can I just want to make sure that I'm not missing something, so hold on 1 second. Yeah. Okay, yeah. So the way to think about this, sorry about that. The way to think about it is to think of this as chi of P and Zi. It's low degree in this. It's not low degree in this. But you can think about it, it's in 0, 1. You can think of chi as like 0, you can think of chi as being in h to the m times f to the m to whatever, to a 0, I'm not sure how to, because maybe, but I'm not sure. But I mean, there is actually. The low degree polynomial is one of them. So the answer is yes, there is. It's the low degree yeah. So it's defined only on H. You can think of it as defined only. This chi is an extension. This chi on its own is extension. What is this chi? This chi is a function. You can okay, sorry. Let me write it differently. Okay, let me fix this. Sorry about that. Instead of this, think of chi. I'm just changing the notation. H1 up to Hm and Z, which is Z1 up to Zm. Okay, I don't want to put it down there. They're both here. And now, actually, I don't. Okay, so what are we saying? We're saying, so this is the extension. So you're saying, what is chi? I'll tell you what chi is. Chi is the extension. Okay, let me rewrite this. Chi and h1 up to hm, z1 up to zm is just multiplication of chi hi zi. So it's exactly the same thing. I just don't want to put hi on the bottom like I did before. So let me put it as a variable. I didn't change anything. And now this what is this? This is the low degree extension of the function. Let me first define chi and h to the 2m. So chi is such that and h to the 2m. So for every hi for every h and z in h to the m, chi hz is equal to 1 if and only if h is equal to z. I only defined an h to the m, now extended. That's how I define chi. Okay, the unique low degree extension. What is exactly the extension? Yeah, it's like this multiplication, blah, blah, blah. I don't want to go into it. Okay, but it's just the unique extension. Okay, so now with that, and the reason there is a unique, actually I should say this is kind of chi 1. And the reason there is a unique extension, this is kind of h1, hi, zi. And the reason there is a unique extension is from the Lagrange interpolation theorem. Okay, so it's just a multiplication of the unique kind of Lagrange interpolation extensions. So all I did here, so sorry about this, but all I did here is I changed the notation from the h kind of as a subscript to h as input. And now I'm doing I'm treating them both symmetrically, which was important because otherwise, so thank you. Wow, you guys are great. So now let's fix the mistake here. So this is chi of p and zi, right? P is, we're summing over p, but zi is an input. That's kind of the input we started with. Like that's the claim. Good, and now, but for me, chi is a low degree polynomial already. So this is just chi of z0 and xi. Thank you. Yeah?
I guess what I still don't understand is, isn't chi not a polynomial in the first variable? Since
Why?
Since the definition for chi, doesn't it only appear in the denominator?
Okay, so let's look at the definition of chi. Right? The definition of chi and m variables is just, so chi takes 2m variables. The definition on 2m variables is just the multiplication. I goes from 1 to m of like a chi 1 and hi and zi. So now I need to define what is chi 1. Oh, you're saying it's 2 variables. It's not, you're saying it's not 1 variable.
Oh, or rather more like in chi 1, like, isn't it not a polynomial in hi?
It's a polynomial. No, I want to think of it as a polynomial in hi and zi. Okay, chi, sorry. Okay, maybe I didn't understand your question. Chi 1 is a 2-variable polynomial. It has 2 variables. So you're right. It doesn't, it's 2 variables.
Yeah.
Not 1, because I said it reduces to Lagrange. You're saying, no, Lagrange is 1. I'm thinking that it's 2. That's what you said, right? Or maybe I didn't.
I guess my question is more emphasizing, like, when we write out the definition for chi 1, aren't we going to get that it's not a polynomial in hi?
No, it is. It is. So I want to.
Won't it be a ratio of polynomials?
No. So okay, you can ask, what is exactly chi I? Chi 1? How do it? Okay, chi is well defined. It's just a product of chi 1s. Okay. Now you can ask, what is chi 1? If you understand what chi 1 is, then you understand what chi is, because chi is just multiplication. What is chi 1? Chi 1 is a bivariate polynomial. It's defined over f2m to f. And how, so now you're asking, how is it defined? Let me tell you how it's defined on h first. So if both of them, first of all, it's a polynomial. It's a 2-variate polynomial. So it's a polynomial and 2 variables, and both its degree, h minus 1. Okay, now you can say, how is it defined on h? On H, I'll tell you. It's 1 if and only if they're equal. That's how it's defined, 0 otherwise. So I defined it on H. Now you can ask, how do I define it on F? So on F, I'm going to define it in the unique way that extends it on H. That's how it's going to be defined. Okay, that's kind of so chi is a low degree polynomial in each and every variable. That's how, before I wrote it like only in Z, but that wasn't good because I needed also to be low degree on H. So yes, Vinod? Oh.
Just the point is that the way it was written down previously, right, had H in the denominator,
yeah.
So it's not a polynomial.
Exactly.
It's not a polynomial.
Exactly.
And here this one is.
Okay.
Okay, so I write it, what's important to me is that chi1 is a polynomial. It's a two-variate polynomial. Both of them are degree h minus 1. Okay, so with that, if we believe, yeah.
If they're not equal, is it 0?
Yeah, yeah. So if h and z are equal, it's 1. If they're not equal, it's 0. Yes, great. Thank you guys. You're great. Fantastic. So now we reduce this big sum to this. Because we sum over the p, so the p becomes z0, this. Okay. Wow, what's going on here? What is the proof? What's the verifier supposed to do? So before he had he needs to verify one little kind of 1 point in vi tilde. And now he needs to verify this mess. Okay, so let's deconstruct. Yes.
Sorry, but is that like, is the argument to like chi is like z0, z1, or zi?
This is a good. Sorry, this is zi. This is the claim we started with. We started with the claim on layer I. Right? You can think of I as 0 in the beginning. But we start with the claim that Vi is equal, the low degree extension of layer I in point Zi. This is the Zi here. Because why is it the Zi? Let's see. What did we say? We said that Vi, we need to argue that it's this. But this is just sum, that's the definition of low degree extension. Sum of the points times this. Let me change this to P Zi. The Zi is fixed. This is fixed. This is from the claim. Good. Now we say, let's sum over the P. So we sum over the P. The P is not fixed. It's summed over. And now we say, let's instead of this, like sum over the two W's, which are the possible kids. All the possible pair of kids. Oh, I think I didn't say. I assume that C is fan in 2. That each gate has only 2 children. And that's, again, with all of the generality, you just increase the depth by log factor. So I'm assuming fan in 2. So it's only 2, each gate has either an addition of 2 or a multiplication of 2. Now, so this is what we get. And now when we do the sum check protocol, the P and the W, so we sum over P, W1 and W2, at the end of the day, we need to compute this polynomial. The verifier will need to compute this polynomial instead of over some fixed P, W1, W2. It's over some, I called it Z1, Z0, Z1, Z2, chosen by the verifier. That's kind of the randomness of the verifier. So P becomes Z0, W1 becomes Z1, and this is Z2. Okay, that's kind of the F there. Yeah?
It's very confusing because then if I is equal to 1 with Z, you're also using that word.
I know.
So that's the different Z. Right?
Yeah, I know. I'm so sorry. These are stars.
Okay, that makes a lot of sense.
It's a constant. So. It's
a constant. Yeah, I know. Sorry, that's a bad annotation on my end. This is a very, very different Z. It's like a totally different animal. These are random Z's chosen by the honest verifier. This is kind of a, I don't know, a Z star that was fixed ahead of time. Okay, so now the verifier needs to verify this. Yeah?
Since V sub I star is fixed,
Mm-hmm.
can't you just use the same chi notation you were before and put it in the subscript of the chi, so then you don't need the extension or whatever, you can just write it out of issue?
The thing is that before I assumed that the chi, when I fixed the h, it was an h to the m. This is in the extension. It's not going to be an h to the m. So I think we should keep the two, yeah. But that's a good idea. Okay, so what is the, so it seems like we had something that looked really kind of reasonable, and we ended up with something that's horrifying. So what does the verifier do now? Now the verifier is like, oh, I just need to verify that this equals some value that we got out of the sum check protocol. So we did the sum check protocol, we got some value, whatever, I don't know what to denote. I'm now scared to denote anything, so this equals something. Now what is it supposed to, he's supposed to verify that. What do you do? So here's the idea, and then we'll take a break. Okay, so he needs to verify a lot of things. First, he needs to compute this add tilde and mul tilde. This goes back to your question. Now, add tilde is a function of the circuit. He doesn't have the circuit. How does he compute these add tilde and mul tilde? Okay, turns out, actually, this is sad news. He actually can't compute. We don't know how to compute. He doesn't know how to compute add tilde and mul tilde. Okay, even if he gets this kind of uniform description of the Turing machine that generates the circuit, he can't compute them. Okay, let's deal with that later. Suppose he has Oracle access. Suppose he can there's a trusted Oracle that lets him compute these values for now. Okay, in the paper it's called like the bare bones protocol. So suppose somehow magically he has a trusted Oracle, but only to compute add tilde and mul tilde. Note, these are only functions of the circuit. They have nothing to do with the claim of the prover. Okay, it's just information about the circuit. It's whether not in the extension, it's whether, this gate is connected by an AND to these two gates, yes or no, or by a multiplication to these two gates, yes or no. So it's not enough for him to compute that. He needs to compute kind of the low-degree extension of that. But this has nothing to do with the prover. This is just a function of the circuit. So first we're going to assume, this is not without loss of generality, but just for simplicity, we're going to assume that V can compute add tilde and mul tilde. Suppose he can. Actually, what we're going to do today is we're going to show the entire GKR protocol, assuming he can compute this. And then only next time we're going to show how to compute this thing. And actually, we're going to show that next time. How can we help him compute it, or how can he compute in a different? How do we deal with this issue? Okay, but for now, let's say he can compute this. Then so the verifier is like, okay, let's see. This I can definitely compute. That's easy. Okay, so the verifier can compute this. He can compute this. He can compute this. And what is he's left? He's left with two things he can't compute. V tilde and I plus 1, V tilde I plus 1 and point Z1 and Z2. Okay, so now, how do we continue? What we're going to say is the following. Suppose in this sum, he was cheated. Namely, the VI value, VI star, is not correct. By the sum check protocol, it means that this entire value is also not correct with very high probability. Okay, I mean, the probability depends on F. You'll take F large enough that, it's going to be with very high probability. So you're left with a false claim. Now what the verifier is going to do, the verifier is going to tell the prover, you know what? Tell me what these two, you gave me something, I don't know what to do with it. Tell me the values, you tell me, the values of VI plus 1 tilde and Z1 and Z2. So the prover comes in, okay, sure. V tilde and I plus 1 and Z1 is VI plus 1 star 1, and V tilde and Z2, I plus 1, is V star I plus 1, 2. Here are the values. Now I'm the verifier. Oh, sorry, I'm the verifier. What do? I check that this, add times the sum of these two values you gave me plus mult times the multiplication of these two values you gave me is equal what we got. Now, by the soundness of the subject protocol, we know what we got is false. It's not true. So the only way, if the prover gives the correct thing, then he will fail. If you give the correct thing, I'll catch him. Because if he gives me the correct thing, I get the true value. But I'm going to check him against the false value. Okay, again, what do we know? He started with a false VI star. We did some section of the subject. We're left with a false. We said that this is something false. Because the soundness of the subject protocol says if you started with a sum that's false, you'll get a false claim about the F. So now I get that this thing is equal to some beta, but this beta is not true. So now I tell him, okay, I don't know how to compute this thing. Tell me what the two values in the low degree extensions are. If you tell me this, assuming I compute this add tilde and mul tilde for now, then I compute this thing. Now, the important thing to note that if this value was false, he must, if he gives me the true values, I'm going to reject them. Because I'm going to compute this thing and check if it's what he claimed it is after the subject protocol. And because he claimed a false value, if you give me the true things, I'm going to reject him. So the only thing he can do if he doesn't want to be rejected off the bat is to give me one of them false, or both false.
He has to give two values.
Right. Exactly. Okay, so where are we? What did we do? After a lot of sweat, we started with a claim on layer I. We did manage to get down to layer I plus 1, as I promised you guys. Here's the price. First, miraculously, we assume he can compute add tilde and mul tilde on its own. Assume. Why? Whatever. Second, we went from one claim about layer I to two claims about layer I plus 1. That doesn't sound very reassuring.
Isn't that where we started?
Exactly. It's where we started. They're like, okay, this is a great time for a break.